Hello everyone, welcome back to another video in our PySpark interview prep series. Today we are diving into an important topic, memory management in PySpark. Efficient memory usage is critical when working with big data, and understanding how PySpark manages memory can make a big difference in the performance of your applications. In this video, we'll explore the strategies PySpark uses to handle memory, including caching, serialization, and garbage collection. Introduction. Uh, in PySpark, effective memory management is essential for optimizing performance and ensuring stability, especially when processing large datasets in a distributed environment. PySpark's memory management model is designed to allocate and control memory usage efficiently across tasks, enabling Spark to handle big data workloads with minimal resource constraints. To achieve this, Spark divides memory into different regions, each designated for specific functions such as caching, execution, and storage. This division helps Spark balance memory needs, allowing it to manage temporary data for processing, retain frequently accessed data for faster retrieval, and optimize storage for final results. Understanding PySpark's memory management approach is key for tuning performance, preventing memory-related bottlenecks, and achieving smooth execution in data-intensive applications. Key components of memory management in PySpark. Unified memory management model. PySpark uses the Unified Memory Management Model introduced in Spark 1.6 to dynamically allocate memory between execution and storage based on workload demands. This model improves memory utilization by splitting the memory pool into two key areas: execution memory, used for tasks like shuffles, joins, and aggregations, and storage memory, used for caching RDDs and data frames. By balancing memory allocation between these areas, Spark can adapt to changing workload requirements, helping to optimize performance and avoid memory constraints during processing. Memory allocation regions. Memory in PySpark is divided into distinct regions within the Java Virtual Machine JVM heap to efficiently handle different types of operations. These regions include execution memory for tasks such as shuffles and joins, storage memory for cached data, reserved memory for Spark's internal metadata, and user memory for user-defined functions. This structure allows Spark to manage each type of data separately, preventing interference between data processing, caching, and internal operations, which helps maintain a stable memory environment. Dynamic memory allocation. PySpark supports dynamic memory allocation, allowing Spark to adjust the amount of memory assigned to executors as tasks require it. If execution memory needs exceed the available allocation, Spark can temporarily borrow memory from the storage pool, releasing cached data to free up space. This adaptability ensures that Spark has the memory resources it needs when performing intensive tasks, providing a flexible memory environment that enhances task execution without compromising stability. Caching and persistence. To reduce the need for recomputation, PySpark allows users to cache or persist frequently used data in memory or on disk. Cached data is stored in the stored in memory region, making it readily available for reuse in subsequent operations by caching data that's accessed multiple times. Spark minimizes recomputation, which saves both memory and processing time. Effective use of caching can significantly improve the efficiency of Spark applications. Garbage collection. PySpark relies on the JVM's garbage collection mechanisms to manage memory automatically. However, tuning JVM garbage collection settings such as choosing between G1 or CMS garbage collectors can help improve memory efficiency in Spark jobs. Effective garbage collection tuning ensures that memory is freed promptly and that unnecessary memory consumption does not slow down tasks or cause out of memory errors. Tungsten execution engine. Introduced in Spark 1.5, The Tungsten execution engine optimizes memory usage by using low-level memory management techniques, including of heap memory management. This approach reduces garbage collection overhead and improves memory efficiency, enabling Spark to handle larger datasets. Tungsten allows PySpark to allocate and manage memory more directly, which enhances performance and minimizes the impact of garbage collection on Spark jobs. Memory tuning parameters. Spark provides several configuration options for fine-tuning memory usage. Parameters such as spark.execute.memory and spark.driver.memory control the memory assigned to executors and the driver, while spark.memory.fraction and spark.memory.storage fraction allow users to adjust the memory split between execution and storage. Spark.sql.shuffle.partitions can also be configured to control parallelism during shuffle operations, impacting memory usage. These settings help users optimize memory allocation based on workload requirements and available resources. Spill to disk. When Spark runs out of memory, it spills intermediate data to disk rather than causing a task to fail. Spilling helps avoid out of memory errors, but it does come with a performance cost as disk I/O is slower than memory access. Efficient memory management, along with well designed data partitioning, can help minimize spills by ensuring that sufficient memory is available for processing without triggering excessive disk usage. Example, configuring executor memory. In this example, we start by creating a Spark session which serves as the main entry point for interacting with Spark's data processing capabilities in PySpark. Here we specify the application name as memory management example to make it easier to identify in Spark's UI. Then we apply two custom memory configurations, spark.executor.memory and spark.executor.memory overhead, which play a key role in how Spark allocates memory resources to executors. The first configuration, spark.executor.memory, is set to 4 GB. This setting defines the amount of memory assigned to each executor, the unit of computation that processes data in parallel on worker nodes. By increasing the executor memory, we provide each executor with more space to handle data transformations, reduce memory related errors, and potentially improve performance for large datasets. This is particularly useful in cases where tasks involve complex transformations or when the dataset is sizable, as it helps ensure that executors have enough memory to perform operations without excessive spilling to disk, which can slow down performance. The second configuration, spark.executor.memory overhead, is set to 1 GB, which allocates additional memory beyond the executor's core memory. This extra overhead memory is reserved for non-JVM tasks such as native code, off-heap storage, and other memory-intensive operations that occur outside of the JVM. By setting this parameter, we provide a safety buffer to handle unexpected memory needs that may arise during execution, especially for operations like shuffling or serialization that can quickly consume memory. The memory overheads prevent out of memory errors and task failures by ensuring that tasks have the extra memory required for processing large volumes of data or performing memory intensive computations. After setting up the Spark session with these custom configurations, we create a sample data frame with a small dataset containing employee names and their respective salaries. This data frame is structured with two columns, name and salary. With the data frame ready, we then perform a filtering operation using the filter method, specifying a condition to keep only the rows where the salary is greater than 4,500. The result of this operation is stored in a new data frame df underscore filtered, which contains the filtered subset of the data. Finally, we call df underscore filtered dot show to display the filtered data in the console. The show method provides a quick way to view the resulting data frame, allowing us to verify the outcome of the filter operation. This example demonstrates how setting memory configurations in Spark session can help manage and optimize memory usage in PySpark. By adjusting spark.executor.memory and spark.executor.memory overhead, we give Spark the flexibility to handle data processing tasks efficiently. Proper memory tuning like this helps prevent memory related errors, minimizes disk spilling, and ensures smooth performance, particularly in cases where large datasets or complex transformations are involved. Example 2, caching data with persistence levels. In this example, we begin by initializing a Spark session which serves as the entry point to work with Spark in PySpark. The session is named example for easy identification within Spark's UI, and get-or-create ensures that a session is created if one doesn't already exist or the existing session is used. We then define some sample data which consists of a list of tuples containing information about employees such as their name, city, and age. This dataset is small but serves as a good example for demonstrating how to work with data frames in PySpark. Alongside the data, we define a schema with column names, name, city, and age to give structure to the data when creating the data frame. Next, we create a data frame from the list of tuples using the createDataFrame method, passing the data and the schema. This transforms the raw data into a structured format that can be easily queried and processed using Spark's powerful data frame API. To improve performance for subsequent operations, we apply the cache method on the data frame, which stores the data frame in memory. Caching is a key performance optimization in Spark as it avoids the need to recompute the data frame every time it is accessed. In our example, the cast data frame df underscore cast is used for both filtering and grouping operations. First, we perform a filter transformation to select rows where the age is greater than 30. We follow this by an action count which counts how many records meet this condition. Since the data frame is cached, this operation will be faster than it would be on an uncached data frame, as Spark can retrieve the data directly from memory rather than recomputing the result. Next, we perform a group B operation to count the number of employees in each city. The group B transformation is followed by the count aggregation function, and the show action is used to display the results in the console. The show method outputs the count of employees in each unique city. This example demonstrates how caching a data frame can significantly improve the performance of subsequent operations, particularly when dealing with large datasets or multiple transformations. By caching the data frame in memory, we avoid the overhead of recalculating it each time it is accessed, which is a key benefit in distributed data processing with PySpark. Example 3, configuring memory fraction and storage fraction. In this example, we set up a Spark session with custom memory fraction settings to optimize memory usage for computation-heavy workloads. The session is initialized with the application name memory fraction example for easy identification within Spark's UI. We configure two key memory-related settings, spark.memory.fraction and spark.memory.storage The spark.memory.fraction setting is adjusted to zero point 0.8, which means that 80% of the executive memory is allocated to Spark's unified memory pool. This pool is used for both execution tasks like shuffles and joins and storage tasks like caching, which is critical for balancing memory between computation and storage in Spark jobs. By setting a higher memory fraction, we prioritize memory allocation for execution, making more memory available for processing operations. This setting is particularly beneficial when handling computation-heavy tasks that require substantial memory resources for efficient processing. The spark.memory.storage fraction is set to zero point 0.3, which specifies that 30% of the allocated memory pool, i.e., 30% of the 80% defined by spark.memory.fraction, is reserved for storage, such as caching data frames or RDDs. This configuration means that 70% of the memory within the unified pool is available for execution tasks. By fine tuning the storage fraction, we reduce the amount of memory dedicated to caching, freeing up more memory for execution tasks to improve performance in computation intensive jobs. With these configurations set, we proceed to create a sample data frame with a dataset of employee names and salaries. We then perform a filtering operation using the filter method to select employees with a salary greater than 4,500, and the filter results are displayed using the show method. This example illustrates how adjusting memory fraction settings allows us to optimize memory allocation in Spark for specific workload types. By increasing the execution memory with the high spark.memory.fraction and reducing the storage fraction, we ensure that computation intensive tasks have ample memory resources, minimizing memory bottlenecks and enhancing performance in data intensive processing scenarios. And that's an overview of how PySpark handles memory management. We've discussed the different techniques PySpark uses to optimize memory, which helps keep Spark applications running smoothly even with large datasets. If you found this video helpful, don't forget to give it a thumbs up, subscribe for more PySpark insights, and hit the notification bell to stay updated with our latest videos. Thanks for watching and see you in the next one.